In this video, I'm going to prove a strange fact. If S equals V1 through Vn is the basis for an n-dimensional vector space V, then this set is the basis for Rn. Now, this is an ordered vector, an ordered basis. So, what you need to notice is that, say, V1, okay, so, look, V sub 1 is equal to, or even V sub I, it is equal to 0 times V1 plus 0 times V2 all the way up to 1 times V1, sorry, Vi, all the way down to plus 0 times Vn. And it turns out that the coordinates of V sub I in basis S is just what we normally call EI. It just has a 1 in the ith row. Okay. So basically, V1 coordinates in S is just 1, 0, 0, 0. So V sub 2 in S is just 0, 1, and then the rest 0. 0 in the second coordinate, all the way down to V sub n, the coordinates in S, why that's just going to be all zeros and then a 1. So I need to show that these vectors are linearly independent and they span Rn. Okay, so suppose A1 times 1, 0, 0 plus A sub 2 times 0, 1, and then zeros. Remember, that's the coordinates of V1 in S. That's the coordinates of V2 in S. All the way down to plus A sub n times the coordinates of V sub n in the S basis. 0, 1. Now, we know that this is, well, this is A1 and then all zeros, and then all zeros except A2 in the second position, all the way down to 0, 0, 0, and then A sub n in the last position, and this is equal to A1, A2, up to A sub n. But if this equals 0, that implies that A1 is 0 and A2 is 0, all the way down to AN equals 0. Because 0, the 0 vector, is really the vector that has all zeros. Say A1 is 0, A2 is 0, all of these are 0, and A sub n is 0. Well, that implies that these vectors, that implied that these vectors are linearly independent. So coming down here, that implies that V1 in S are the coordinates of vector 2 in respect to the S basis, all the way down to the coordinates of vector n in the S basis. This set is linearly independent. Now, to show that it's a base, to show that it spans Rn is easy. Let V be in Rn. So V is equal to, R1, R2, up to Rn. But this is nothing more than R1 times 100 plus R2 times 01, all zeros, all the way down to R sub n times 00, and then 1. But for completeness, that's R1. Now this is V1 coordinates of S plus R2 coordinates of V2 in S, basis all the way down to R sub n are the coordinates of V sub n in S. And again, it equals V. Now, this is in Rn, that's in Rn, that's in Rn, that's in Rn. When you multiply them by the scalars, that's in Rn, and the whole sum is in Rn, and so is V. So I was able to write V as a linear combination of vectors in Rn. All of these are in Rn. All of these are in Rn. Okay, so V can be expressed as a linear combination of the vectors V1 and S all the way down to VNS, all of which are in Rn. So, time to give this a name. So T spans Rn, and T is a linearly independent set in Rn. So we have that T is a basis for Rn. Not, mind you, not the basis that this set came from. This set came from the vector space V. Okay? We have that this set is not a basis for vector space V, but rather vector space Rn. That completes this proof. If you love videos like this, please subscribe to my channel. Always looking for new members. Tell your family and friends about my channel, your teachers and classmates. Most of all, watch and learn. I hope to see you in the next video.